Good morning. Today we will study inner product spaces. All right. So let me explain you about the inner product, and then we talk about inner product spaces. But before that, I would like to remind you about dot product because that is very important example of inner product. Okay. So let's consider Rn, and you consider two vectors u and v in Rn. So suppose that u is u1, u2, and un, and v is v1, v2, and vn. We know how to find the dot product of u and v. Okay, dot product of u and v, that is just u1, v1 plus u2, v2 plus so on plus un, vn. And by the way, we can remind you about the norm or the length of a vector. So that is square root, right? Or let's say we already know dot product, so I can write just very short u dot product with the u, and then power 1/2, right? So we can measure the distance between u and v. That is just the norm of the difference. That is the distance between u and v, right? The norm of u minus v. So everything looks good with dot product. And last time we learned not only this distance, right, measure, we still know how to measure the angle between two vectors. So the angle between u and v can be found using the following formula: cos of theta equal to dot product of u and v divided by the norm of u times the norm of v, right? Or theta is just a cosine of this value. Once we know the angle, we can determine the orthogonality, right? We say u is orthogonal to v if the theta is equal to pi over 2, or the dot product of u and v is equal to 0. So we already have some geometry with the dot product. Make sense? That is very important. As I mentioned previously, when we study vector spaces, we only know algebraic structures. We didn't have any geometrical properties, geometrical structure. But now, with the dot product, we are good. We can determine orthogonality, we can determine angles, we can measure the distance between two vectors or 2 points. So we can do whatever we want with a vector space if we determine the dot product. And dot product is very special case of inner product. So we can go ahead to define the general inner product. Okay, definition of inner product. So that is just a map, is it correct? First thing, that is just a map. You can see from here, the dot product is a map. The dot product is a map. And this map defines on Rn times Rn, right? I would say, okay, let me write this. This is just a map. If we just consider dot product in here, that is a map from, I write like this, from Rn to R, right? Because if you have vector u and v in here, you can determine dot product of u and v, and that is just a number in R. So inner product is also a map. Okay, it's also a map. First thing is a map. I can write like this, a map from Rn times Rn. What's that? That is Cartesian product, right? Cartesian product means this is the set of all pair uv where u and v are elements in Rn. All right. I just take Rn, you know, as an example, but in general, you may want to write like this. That is just, you know, a map from V to here. I consider only, you know, real maps, okay, real values map. So this map should satisfy the following properties. The first property, in the product of U and V is just equal to VU. So when you interchange U and V, you don't change the value. The second property, U in the product with V plus W, that is equal to UV plus UW. Okay, and then the third property, you have a constant in here. You multiply a constant with the inner product U and V. You can just bring that constant in. So that means, you know, if you have a constant C inside, you can take this out, right? You can take this out here. And the last property, V inner product with V is always greater than or equal to 0. And equality happens if and only if V is 0. So you can see that actually dot product satisfies all these properties. And I want to mention one more thing, right? We consider only maps, right, that text value in R. So in case if you go, you know, high level courses, you can see inner product but with the complex numbers. So for complex numbers, some properties will be changed, okay, but right now we just work with real numbers. All right, so this is very, you know, very simple definition, right? And we say we mentioned that, you know, dot product is actually an inner product. For the first property, of course, is obvious. The second property is also obvious. The third property is also obvious. And the last property is also obvious, right? Because dot product is always of a vector on itself is always greater than or equal to 0. And equal to 0 if and only if that is 0 vector. All right, so we might have another examples. Let's do this. Example. Another example of inner product is, now I can define, you know, on, let's say on R2, let's define the following map. The map is, let's define the map from R2 times R2 to R, such that you have U and V in here. That is, you know, U1 V1 plus 2 U2 V2. So if in this place we have 1, so that is just dot product. Now I don't want that. I want to, in this situation, I want to define a new map, a new product, and see if this will be an inner product or not. Okay, so let's check if this product is an inner product. We just need to check 3 properties. The first 4 properties. The first property, we have UV. By the definition, that is U1 V1 plus 2 U2 V2, right? But at the same time, we have VU. What is that? That is U1, let's say V1 U1 plus 2 V2 U2. So from here I can see actually UV is equal to VU. That means the first property satisfies, right? Let's move to the second property. Second property is if you pick 3 vectors U, V plus W, you need to check if this equal to UV plus UW. If that is the case, so the second property is satisfied. Okay. All right. So the left hand side part is what? Is by definition that is U1 V plus W. I write this 1 in here. Okay. Plus 2 times U2 V plus W, the second coordinate. But what is this? What is the first coordinate of this vector? That is just V1 plus W1, right? So I have this U1 plus 2 times U2. And this is nothing but, you know, V2 plus W2. All right. I thought this out, okay? I get U1 V1 plus U1 W1 plus 2 times U2 V2 plus 2 times U2 W2. And I will group U1 V1 and U2 V2 together. U1 W1 and 2 U2 W2 together. So I will have the following. I have U1 V1 plus 2 U2 V2, right? Plus U1 W1 plus 2 U2 W2. And by the definition, this is UV, right? That's just product UV. And this is the product of UW. So basically, we just prove this identity. Make sense? So the second property also satisfies. Perfect. Let's move to the third property. The third property says if you multiply product with C, right? So you can print C in or out. So you have CUV. We just need to write out, you know, explicitly. So the left-hand side part is what? Is C. By the definition of product of U and V, you have U1 V1, right, plus 2 U2 V2. Okay, so what is that? That is C U1 V1 plus 2C U2 V2. But now, if you group these sums like this, CU1 together, right, and CU2 together. So basically, that is, it's just CU and then V. That means we just prove the identity in the third property. So the last property is U and U greater than or equal to 0. But it seems like this is obvious because by the definition of this product, U product with U is just U1 squared plus 2 U2 squared, which is always greater than or equal to 0. And equality happens if and only if U1 equal to U2 equal to 0 or U is 0 vector. So that means this is an inner product. I don't know if this surprises you or not, but you know, here's an example that we might have many inner products, right, in a vector space. So dot product is just very special case. And with dot product, of course, we can do a lot of things. But again, we may define different inner products. Right now, we have another inner product, right? But I'll tell you, not every product will be inner product. Makes sense? Here's the case. If I just change this, look at this. If I just change in the definition, in this definition, right? I just replace the plus with the minus. So we still have a product, but that is not in the product anymore. Let's check that, right? Let's check that. So let's say this is example 3. I'll define on R2 another product, okay? Which is if you have U and V, each U and V go to U1 V1 minus, let's say 2 U2 V2, and this is not in the product. we can check all the properties, right? We can check 4 properties and see which one is not satisfied. But the obvious one is the last one. I can say yes. I can say the last one is not good. Why? So let's say you need to see that, you know, product of u and u greater than or equal to 0, right? Makes sense for any u. But what is u product with u in this case? That is just equal to u1 minus 2u2 u2, which is u1 square minus 2u2 square. There's no guarantee that, you know, this guy is always greater than or equal to 0. You can pick u1 equal to 0 and u2 equal to 1 as an counterexample, right? You plug 0 and then you get 0 square minus 2 times 1, which is negative 2, less than 0. So that means the last property is not satisfied, right? So this is not an inner product. All right? So, you know, that is very important. And I would not say that dot product is the best one. Makes sense? So in mathematics, you can define whatever you want, and the most important, that works. And then that works in most of the cases. And then, you know, that's why people use this theory. Makes sense? All right, let's consider another example. We just work with Rn, right? And now let's work with Mn. Set the vector space of matrices of order n. So we know that Mn can be spread out like R n squared, right? For example, you want to determine a matrix 2 by 2, so you need 4 numbers, right? 2, 1, 8, 2, 2. So you can write, yeah, that is maybe equivalent to a vector like A11, A12, A21, and A22. Just write all rows in a row form, so you get that vector. So basically that is, you know, in R2 square, which is R4. Makes sense? And so, you know, if you consider dot product of two matrices, so you might think like this. Okay, I have one matrix A, which is A ij. Okay, I have another matrix as B ij, so I can find the product, the dot product. Let's say that the dot product. Okay, it's very naive dot product of A and B like this. A dot B is just equal to, you know, sum of A ij B ij, where ij from 1 to n, right? You just take product of corresponding entries and then sum them up. You get a dot product. Okay, or you get an inner product. Let's say that. I will write here in scope, you know, like this. Of course, you may define another one, and, you know, once we know more about matrices, there are other inner products, right, which are more important than this one. Another example. So, you know, today we have a lot of examples. Let's talk about the space CAB. The space CAB, that is the space of continuous function, right, on AB. So in this space, you may define the following product. Let's define the product f g is equal to integral from a to b fx dx gx dx. It's just integral of product. Let me write that clearly. Gx. All right, now let's check if this is an inner product in CAB or not. Okay, so question is inner product the first property fg equal to gf. Let's check this. Okay, so what is fg? By the definition, I write here that is definition. Fg is equal to integral from a to b fx dx. Again, fx gx, right? Gx dx. But you know, what is the right hand side? Okay, let me write that. Right hand side is integral from a to b gx fx dx. So basically you can see these two integrals are equal, right? Because f and g are commuting, so everything's good with the first property. Okay, all right, the second property, you need to check if you have fg1 plus g2 and the product of f with the g1 plus g2 is equal to fg1 plus fg2. Okay, so okay, we check this again. Let's consider the left hand side part. The left hand side part is just equal to, you know, by the definition, that is integral from a to b f of g1 plus g2, right? I write without x, just for, you know, just in short. This is ab f g1 plus f g2 dx. Since we can break this integral into two, we have ab f g1 dx plus ab f g2 dx, and the first term is nothing but the product f g1, right? The second one is the product of f g2. So basically you have f g1 plus g2 is equal to this. That means this property is also okay. We are good with the second property, right? Let's move to the third property. The third property is just scalar multiplication. So I have CFG equal to CFG or not, right? Let's check that. So what is CFG? That is C integral from a to b fx gx dx. So since this is integral, you can take C in or out, whatever you want, right? So that is just AB CF, I write like this, x gx dx, right? And of course this is just equal to the right hand side part by the definition. All right, the last property, property 4, ff greater than or equal to 0. So what is ff? ff is integral from a to b fx gx, no, not gx, g in this case is f, right? So we have that is equal to integral from a to b f of x squared gx. Of course this is greater than or equal to 0 because, you know, f of x squared is always greater than or equal to 0, and the equality happens if and only if when f of x equal to 0. Done. So that means this is an inner product. That is an inner product. Okay. So we still have one more example on the vector space of polynomials. Let's do that, and then we move to properties of inner product. All right. Let's consider one more example. Let's consider P2, right? The vector space of polynomials with the degree less than or equal to 2. Okay, so we know each polynomial in P2 has the form ax squared plus bx plus c, and we also learned that for each one like this corresponding with, you know, just vector a, b and c, right, in R3. So basically if you define an product in R3, so you can just, you know, associate that product with P2. like dot product, right? Like dot product. Let's say like dot product. So we know dot product in R3 is what? You have A1, B1, C1 dot product with A2, B2, C2 is A1, A2 plus B1, B2 plus C1, C2. So you can do for polynomial P1 x a equal to ax squared plus bx plus c, and P2x equal to a1 b1 c1 a2x squared plus a b2 x plus b wait c2, okay, c2. So you can define dot product between two polynomials like this: P1, P2 equal to A1, A2 x squared plus B1, B2 x plus C1, C2. Right? And just go ahead to check everything, all properties of dot product or inner product. So you get what you need. Okay? So basically, we have examples with our well-known vector spaces like Rn, Pn, CAB, and matrices. Okay, now let's move to more properties of inner products. So the first property is obvious. Inner product of 0 with any vector is just 0. Of course, since you can interchange u and 0, so you can write this just u and 0 in here. What does it mean? It seems like we can determine the orthogonality. Okay, I just write in here. Orthogonality. We talk about orthogonality when we study dot product. And then, since dot product is a special case of inner product, so we have right to consider orthogonality with respect to an inner product, right? So you say, yeah, maybe we say that like this: two vectors are orthogonal if their inner product is 0. So that means they are not orthogonal in the sense of dot product, but they are orthogonal in the sense of inner product. There's nothing wrong with that. Makes sense? That's product. That's our product. So we can determine product we want. That means we can define orthogonality as we want. Don't forget about that. Makes sense? Second property. So we talk about u plus v and w, right? That is equal to uw plus vw. In the definition, we talk about u, v plus w. That is about the definition, right? But in here, yeah, if you interchange, oh my goodness, not really clear in here. Yes, if you interchange u and v and w like this, you are also okay. And the third property, like if you have c u in here and cv, means c in the position of v, right? Not in the position of u. So you still can take this out. But I mentioned again, right? All this property works when you consider real value dot product or inner product. If you consider complex value inner products, those properties will be changed regarding the complexness. Make sense? So you will involve you would involve like conjugate of inner products in here, but we don't do this in this course. All right. So as I mentioned about orthogonality, right? We are ready to determine the length, the distance, and the angle and orthogonality of two vectors with respect to any inner product. Okay, so now let's work on geometry. Uh, so you have a vector space. Okay, you have vectors via a vector space. In this vector space, you have an inner product. Okay, an inner product. So a vector space together with an inner product is called an inner product space, right? So if V is vector space and we have an inner product on that, we will have an inner product space. All right. So on this inner product space, now we don't have any dot product, right? Dot product is just a special case of inner product. We have right to talk about the geometry of this. So what kind of geometry in here? First, I can determine the norm or the length, right? The length or the norm of a vector. So I say, yeah, what is the norm of U? The norm of U is just inner product of U and U, right? And I apply 1/2, just square root, right? I may divide the distance between two vectors or 2 points in this inner product space. So that is what? The distance again, distance between U and V is just equal to the norm of U minus V with the norm, in this inner product space. And then I can find the angle between U and V, right? The angle between U and V is, I write here, that's just a cosine of what? A cosine of the inner product of U and V divided by the norm of U times the norm of V, right? You can see, actually we use all formulas from dot product, right? And then the last one is orthogonality. We say U and V are orthogonal if the inner product of U and V is equal to 0. So it looks good, right? And we might define unit vector, okay? That is U divided by, that is U divided by the norm of U, where the norm is defined using the inner product. So, here's the thing. You may have a unit vector with respect to one inner product, but that is not unit vector with respect to another inner product. Okay, let's talk about that, right? Here's an example. Let's pick the very first example about dot product in R2. With the dot product, you have UV is just equal to U1 V1, right, plus U2 V2. So the norm of U in this case is just square root of U1 square plus U2 square. Okay, so if this is a unit vector, right? If U is a unit vector, the norm is 1. That means U1 square plus U2 square root is just 1. Or from here you get U1 square plus U2 square equal to 1. What is that? That is the circle, right? Center at the origin. This is 1, this is 1, this negative 1, and we usually call this unit circle, right? Unit circle. So this is unit circle. That's good. And that is, the set of all unit vectors in R2 with respect to dot product, with respect to this dot product. Now we define another product we just seen previously, that is u1 v1 plus 2 u2 v2, right? So the difference is in 2. All right, so let's say if the norm is 1, what's that? Oh, but first I need to find the norm of u, right? That is u1 square root of 2 times u2 square. Make sense? All right, so if we put this equal to 0, just 1, right? Unit vector with respect to this in the product. So you get u1 square plus 2 u2 square equal to 1. You see, you don't have a circle anymore. Makes sense? So this is an ellipse. This is an ellipse. So you have u1 square plus u2 square over 1 over 2 equal to 1. So this is an ellipse. You see that, with respect to different inner products, you might have different set of unit vectors. Don't forget about that. And that is very surprising. Makes sense? You might think like this. When we study basics and we study, changing basics, you need to apply some transition matrix, right? And the situation may be similar to inner products. So when you go from one kind of inner product to another kind of inner product, you might need to change that. So that's why, with respect to different inner products, you might have different sets of unit vectors. So that is common thing. Makes sense? All right. Let's work on more examples about inner products. I think that I can finish a recording for the whole sections, but that would be 2 lectures. Okay. I think we'll do that right now. We don't have to postpone. Let's consider examples about inner product. So I have 2 polynomials, P, which is a0 plus a1x plus so on plus an x to the n, and Q is b0 plus b1x plus so on plus bn x to the n. Of course, this is vectors in Pn, right? The set of vector space of all polynomials of degrees less than or equal to n. And we just talk about, the dot product of P and Q. That's just a0, b0 plus a1, b1, x plus so on plus an, bn, x to the n. So this is obvious. But we would like to do with concrete polynomials. Okay? So I would mention this is just kind of dot product. Dot product of, because we know, right? We know that Pn is, isomorphic to, kind of isomorphic to what? To Rn plus 1. We need n plus 1 numbers to determine a polynomial in Pn. So, that is nothing but, the dot product of vectors in Rn plus 1. Make sense? Let's say I have two polynomials or 2 vectors. Let's say P is 1 minus 2x squared and Q is 4 minus 2x plus x squared. Another polynomial is R is x plus 2x squared. Let's find the following. First one, product of P and Q. So product of P and Q, by the definition of this, I will have just 1 times 4 plus 0 times negative 2x plus negative 2 times 1x squared, which is 4 minus 2x squared. That's it. That is product of PQ. Second one, you can find the length of R, right? What is the length of R? Regarding this in the product, you can find the length of R easily. So here's R. R is corresponding to, I would write like this. That is 0 plus 1 times x plus 2 times x squared, right? So by the definition of this inner product, I have the norm is equal to square root of 0 square plus 1 square plus 2 square, which is square root of 5. Okay, and then I can determine the distance. Let's say the distance between P and Q. That is the distance. That distance is equal to norm of the difference, right? So I just take the difference between P and Q. What is that? Or basically I just subtract, right, corresponding coefficients and then apply the formula of the norm. So I write that in short, square root of what? I have for the free coefficient, I have 1 in here, 4 in here. So I would get 1 minus 4 square plus the second one. I have 0x in here, but I have negative 2x in here. So basically I will have 2 square in here and plus for the x square I have, you know, negative 2 in here and 1 in here. So I will have 1 I have 1 plus 2 minus negative 2 is plus 2. Okay, and thanks to this we get, you know, square root of what? Of 9 plus 4 plus 9. All right, so which is square root of 22. We can check. Let's say the angle between let's find the angle between Q and R. Okay, Q and R. Say the angle of Q and R. So based on that definition, I can find the angle, but you know, we need to find cosine of theta, cosine of the angle between Q and R. That is Q R in the product divided by the norm of Q and the norm of R. Okay, we just have the norm of R, which is, you know, square root of 5. We need to find the norm of Q. All right, let's find the norm of Q. Let's look back. What is Q? Q is 4 minus 2 plus 1. So the norm of Q is equal to 4 square plus 2 square plus 1 square, which is 16, 20 square root of 21, right? And then we can find the inner product of Q and R. Did we do that? Not yet. The inner product of Q and R is 4. Okay, let is 4 in here. But here you have 0. So let me write here 4 times 0 plus negative 2 times 1 plus 1 times 2. Oh, that is 0. Perfect. Let me write here 4 0 plus negative 2 times 1 plus 2 times 1 equals 0. So what does it mean? That means that, you know, Q and R are orthogonal, right? Q and R are orthogonal. Of course, the angle is theta is just pi over 2. Even you don't have to find, you know, we can skip this step, right? Just dot product, inner product. All right, so let's move to C01. Okay, let's move to another example with C01. Let's calculate inner products, right? And the distance between two functions. So we consider set of all continuous function on 01 with the standard inner product. Let me remind you that we say fg in here, that is integral from a to b, in this case from 0 to 1. In here, fx gx dx. Okay, so if you consider the function fs x plus 1 and the g x is equal to x squared. Let's find all informations about f, g, distance, angle, and orthogonalities, everything else. Okay. All right. So let's find the norm of f. What is the norm of f in this case? So that is integral from 0 to 1 f of x squared, right, dx, and apply 1 over 2. Okay, so you have integral from 0 to 1. I have x plus 1 squaring here, dx, and square root. That is nothing but, 1/3 x plus 1 cube 0 from 0 to 1, and apply 1/2, right? So that is 1/3. You plug 1 and 0 into this, you get 2. Oh, what's wrong with this? So you get 2 cube minus 1 cube, right? And 1/3 in here, and then you apply 1/2. Okay, that is 1/3, 7, or 7 over 3. That is 7 over 3, and then square root. That is the norm of f. You see, that's how we can find. All right, let's find the norm of g. The norm of g, again, that is integral from 0 to 1 gx squared dx, and then apply 1/2 square root in here. So that is integral from 0 to 1, g is x squared, and then with the square you have x to the 4 dx to 1/2, and then you get 1/5 x to the 5, x to the 5th, and then evaluate it from 0 to 1, then 1 over 2. So you have 1/5, 1/2, or 1 square root of 5. Okay, this is square root of 7 over 3. The norm of f, the norm of g. It looks like, the norm of g is smaller than the norm of f, right? But that's nothing special. You can see that g is square and f is just, a linear function, but the norm of f is bigger than the norm of g. Of course, it depends on how we define the inner product. All right, and then you can find the distance between f and g. Let's do that. The distance between f and g. Okay, the distance between f and g is norm of f minus g, or I can write integral from 0 to 1 f minus g squared in here, right, dx, and then square root. So I have 0 and 1. F is x plus 1 minus x squared in here, square dx 1/2. Okay, so now we just for this out, and wow, we get a very huge integral. 0 and 1. So I have x to the 4 plus x squared plus 1 minus 2x cubed minus 2x squared, and then plus 2x dx, and apply square root. So I will evaluate each terms in here. Okay, I have, okay, without this I got right like this, and then 1/2 x to the 4. I have 1/5 x to the 5th with negative, okay, I write here negative 2/3 x, no, negative 2 to the over 4, okay, x to the 4. With the square, I have 1x squared in here, and then with negative x squared in here, so I have negative x squared only. For the negative x squared, I have 1 over 3 x cubed, okay. With 2x, I get 2x squared over 2. With 1, I would get just x, right? Okay. Oh my goodness. Okay, that's fine. And this evaluated from 0 to 1. So basically at 0, the function is 0. At 1, I will have all values in here. Just 1/5 minus 1/3 plus 1 minus 2 over 4 is 1/2 plus 2 over 2 is just 1. And then square root. So let's calculate this carefully. 1 with 1 is 2. 2 minus 1/2 is 3/2, minus 1/3, and then plus 1/5. So the common denominator is 30, right? I have 10 in here, minus, I have I have 45, minus 10, plus 6. Okay, so that is 35, 41 divided by 30 and square root. So that is the distance between F and G. Make sense? How about the angle between F and G? Let's calculate the angle between F and G. The angle, now you see it's interesting, right? Angle between two functions. But again, when we're talking about vector spaces, each element in that vector space is a point. Don't forget that. So whatever that is matrix, that is vector, or that is a function or matrices, they are points in a vector space, in their vector spaces. So that's not something very surprising, right? So for the angle between F and G, I need to find cosine. That is inner product of F and G times F divided by norm of F and norm of G. We already have norm of F and norm of G, I guess. In here, yes, we have that. So now we just need to find inner product of F and G. Okay, inner product of F and G is integral from 0 to 1, x plus 1, x squared dx. Okay, that is integral from 0 to 1, x cubed plus x squared dx. And then that is equal to 0 to 1. Oh no, we evaluate that right away. So that is 1/4 x to the 4 plus 1/3 x cubed. Evaluate from 0 to 1. And then I have 1/4 plus 1/3, because at 0, this function is 0. So basically that is 7/12. So that is the inner product. And then the cosine of theta is equal to inner product divided by the norm of F. Let's say, what is the norm of F? The norm of F is square root of 7/3, and another one is 1 over square root of 5. Square root of 7/3 times 1 over square root of 5. So you have 7/12 times square root of 15 over square root of 7. You can simplify 7 with the 7 and maybe square root 3, but yeah, that's fine. 5, I get square root of 105/12. So that is the cosine between two vectors F and G. And then from here you can find theta is a cosine of square root of 105 divided by 12. And it seems like that is not pi over 2, right? So because dot product is not inner product is not 0, so these two vectors, two functions, are not orthogonal. All right, so we still have some inequalities for this. Let me remind you about that. Okay, as we learn, inner product and some properties, some inequalities. I can write here some inequality. All right, so the first one is Cauchy-Schwarz inequality. Cauchy-Schwarz. It's a U and V. The absolute value of inner product U and V less than or equal to U and V. I think we explained about this. This is because of this of the cosine. Cosine takes value only between -1 and 1 because of this formula. This is only between -1 and 1. So that's why whatever you considering here in the products, right? That is similar to dot product. We still have this inequality. The second one, triangle inequality. So you have u plus v less than or equal to u plus v. So we have triangle in here. With the dot product, that's okay. But within the product, we also have norm of this with respect to inner product. Another one is u, and by the parallelogram law, u plus v is this, u plus v, and have the norm in here. So it says, the norm of this guy, the length of this guy less than the length of this guy plus the length of this guy. Because this is, that is v. All right, and if f and g, if u and v are orthogonal, we will have Pythagorean theorem. If u is orthogonal to v, then we have u plus v square equal to u square plus v square. The picture is like this, right? That is u v norm, right? That is u, that is v. That's it. If the angle between u and v is pi over 2. All right, so I will not show you some examples regarding inequalities because we already did that with dot product. We don't need to verify them anymore because they are just similar, right? Now I go ahead to tell you one of the most important in this topic, that is orthogonal projection. Okay, and we will use orthogonal projection in inner products to find an orthonormal basics and an orthogonal basics from any basics. Okay. Orthogonal projection. I don't know if you learn this in calculus 3 or not, but anyway, we have this in here, and we need this, in the rest of this chapter, right? So let's say we have two vectors u and v, okay, u and v in here. That is the origin, that is v, and you want to find orthogonal, projection of v onto u. So I say that is orthogonal projection of v onto u. So how do that? But before we discuss about how to do that, I would like to discuss about the meaning of this. Imagine if you look at this v, as a point, right? So you have one, for the u, you have a straight line. You have a straight line here. You have straight line here. So what is orthogonal projection of v onto u? That is the closest point to v on this straight line, right? That is closest point to v on the straight line, on this straight line with the u. Make sense? So that is some kind of optimization problem. That means in order to solve that problem, in order to find this orthogonal projection, so you can pick any point in here, right? You can pick any point here. Okay, let's say x, and so the distance from x to v is always greater than or equal to the distance between v and orthogonal projection of v onto u. So orthogonal projection is a solution of optimization problem. Don't forget about that. That is solution of an optimization problem. Okay. So that's very, very important. Makes sense. And here I can prove the formula easily, but you know, I just go ahead to tell you. I just go ahead to tell you the formula. All right, just go ahead to tell you the formula right here. The formula is projection of V onto U is just dot product, inner product. I'm sorry, inner product of VU over the norm of V square times the norm of U square, times U. So that is some kind of vector in the direction of U, right? But the coefficient look like this. That is the coefficient. Okay. So let's consider the following example. I have two vectors U, just 4 and 2 in R2, and V is 3, 4. Now let's find with the standard dot product, okay? Just standard dot product. So we can define orthogonal projection of U onto V. What's that? That is U dot product with V divided by V square norm and then times V, which is 12 plus 8 over the norm of U is what? Is 4 square plus 2 square, and then the norm of V is 3 square plus 4 square, and then times 3, 4. So that is 20 over 16 plus 4 is square root of 20, and this is 5. So times 3 and 4. So basically, I do something wrong in here. We have square of the norm of V. So that's why we don't have this part. Sorry for this. And we have square here. You know, that is common mistakes. Usually I also do, and my students too. So let me point out the mistakes, right? That is difference with the cosine, okay? With the cosine. For the cosine theta, you have like U and V in here, okay? That's why, you know, I mess up in here. So let me erase the mistakes here. I have 5 only, because 3 square plus 4 square is 5 square. I think I have 5 square, so I have 25. So basically I will have 12 over 5 and then 16 over 5. Alright, so that is orthogonal projection of U onto V. Now let's find orthogonal projection of V onto U. Okay. That is again UV divided by the norm of U square. So if you have U in here, so that is the norm of U square, right? And then multiply with the U. We already have dot product of U and V. That is 20. And we just found the norm of U square over there. So that is 4 square over 2 square. Square root and square. So square root just disappear. Multiply with the U is 4, 2. Okay. So basically, interesting. Basically, you get the same vector, right? So it looks very interesting. You get the same vector. So the vector like this, that is also U. The vector might looks like this. And this is orthogonal, because orthogonal projection of V onto U is the same with the U. Right? This is the angle between V and U. So V and U are not orthogonal, but U will be the orthogonal projection of V onto U. You know, we can do some examples for R3, and maybe one example with C, AB. Okay, let's do with CAB, right? Because R3 is almost the same. Let's consider another example with the CAB. Okay, so let's say f of x is 1, g of x is x, and we consider, let me write that in here. Let's say not CAB, I just pick 0 and 1, okay? 0 and 1. Now we can define orthogonal projection. Find the orthogonal projection of f onto g. So by the definition we have, that is just inner product of f and g, right? Divided by the norm of g square times g. Okay. So what is the inner product of f and g? That is integral from 0 to 1 f of x g of x dx, which integral from 0 to 1 times x dx, and that is 1 over 2x squared evaluated from 0 to 1. So you get 1/2. And then the norm of g, that is f g inner product. The norm of g is integral from 0 to 1 g of x dx, and then apply square root in here. So basically you get 0 to 1 x squared dx 1/2, and that is 1/3 evaluated, x cubed evaluated from 0 to 1, a half in here, and you get 1/3 square root. All right, so we have all informations, right? We just plug everything into the formula. So I have 1/2, I have square root of 1/3. Let me write this in here. So that is 1/2 on the top, in here square root of 1/3, but apply square, so I have 1/3. Okay, I have 1/3 in here. I have 1/3, and g is x, so basically I have 3 over 2x, and that is a orthogonal projection of g of f onto g. Of course, you can find orthogonal projection of g onto f if you want to. Let's do that, and then we finish today's lecture. All right. Let's find orthogonal projection of g onto f. So again, that is fg in the product divided by f squaring here, and then f. What we already have in the product of f and g, 1 over 2 over there. We just need to find the norm of f, right? The norm of f is equal to, let's say the norm square, okay, is equal to integral from 0 to 1 dx, which is x evaluated from 0 to 1, that is just 1. So we plug 1 and the inner product 1/2 into this formula. You get just 1/2 over 1 f, which is 1. Okay, I write here, which is 1. So the answer is 1/2. All right, so I think we have very long video, but this video would cover 2 lectures, today lectures and lectures on Monday. So please watch them and do homework. If you have any questions, please feel free to let me know and set up a Zoom interview with me, right? I try to be available for you per request. All right, thank you, and hope you be safe.